Hi, my name is Travis English, and this is the audaciously titled Fundamentals of HVAC Risk Management Controls for Pandemic Scenarios. So we're kind of at this point of what did we learn from the pandemic? What could we do better next time? How should we be preparing for the future? And that's a lot of what I'm working on. In my opinion, the biggest problem that we had in 2020 wasn't a lack of air or a lack of filters. We had lots of air and we had lots of filters. And maybe more importantly, we were able to get more and deploy more very quickly. The biggest problem that we had was figuring out where we needed it and what we needed and where we didn't need it or how much we needed. So the whole range of questions, is this room safe? Is this room safer than that room? What do we need to do to make this room safe? Or should I do this? Should I do that? Which one of these gadgets is better? How much better is this gadget than that gadget? We didn't have a framework for comparing those options, so it's difficult to answer those questions with any confidences. In a lot of cases, we just did more. It's very easy to say, I want more. Let's just do more air, more filters, more negative pressure. We did a lot of more, but more isn't always better. And in the future, we need to be smarter. We need to do a lot more smarter than more. Engineering controls are the middle element of this controls hierarchy. If you've ever seen this controls hierarchy of occupational safety or environmental hazards. So engineering controls are yellow. Some definitions. Engineering controls are strategies designed to protect workers from hazardous conditions by placing a barrier between the worker and the hazard or by removing a hazardous substance. Yes, that's the Wikipedia definition. The CDC definition is right below it. And there's another 4 or 5 definitions that you can find out there. In my opinion, I don't know that any of these definitions are fantastic because in my conversations with doctors and infection control practitioners and even occupational safety, these definitions miss the component that I hear the most, which is that engineering controls need to be highly reliable and repeatable. So to our audience, engineers, that's what the engineering controls represent. Every time I put an aerosol into the room, this room should do the same thing. If this room is supposed to remove 80% of contaminants in 20 minutes, it should always do that. So the word engineering implies that high level of repeatability and reliability. And of course, that's why we use the color yellow, right? The color of yellow for engineering is the same as the engineering color of yellow for the USS Enterprise 1701D. These guys, in my mind, are reliable, repeatable, right? Good folks. So my premise here is that more isn't necessarily better, better is better. So in the future, we don't need more air or more filters or more negative pressure. We need better engineering. We need more quality in engineering. We need better explanations, better tools, better comparisons, better predictions, and higher reliability. So this is going to be an engineering presentation, folks. We're going to get technical. There's even an equation, a couple slides in here that has some calculus on it. I know there's engineers in the audience, and so I'm going to show the details. If you're on this call or watching this video and you don't have a degree in mechanical engineering, please stay, please hang on. I did give this presentation last week to a more diverse audience, and it's not too bad. Nobody's head exploded. I will tell some jokes along the way. You're going to hear some jargon, but it'll never last long. So bear with me for a minute in each case, and we'll always sort of come up for air, pun intended, at the next slide. Here's my basic premise on engineering controls. So this is a Travis definition. Every engineering control that we deploy should have a measurable effect on the behavior of aerosol contaminants. During design, our job is to predict the measurable effect on the behavior of aerosol contaminants, and then during commissioning, our job is to validate or measure that effect on the behavior of aerosol contaminants. This is the bottom line. In the future, design engineers should specify pass-fail field testing. If a situation is important enough to warrant an engineering control, then it's worth doing a field test, and it needs to pass the field test. So when we say behavior, what are we actually talking about? What are these behaviors? There's 3 basic varieties of engineering controls and 3 types of behaviors, and therefore 3 types of tests. By the way, if anyone can think of a 4th, let me know. So the 3 types are capture, containment, and removal. And of course, there's always an asterisk right away. There's an asterisk next to removal because it can actually be removal or deactivation. If we're dealing with room ventilation or filters, we're going to talk about removal. But in a couple places here, we're going to talk about UV systems or other like decontamination or killing technology. And in that case, we'll use the word deactivation. But the math is the same. The sort of fundamental equation is the same. Let's roll through these three types of tests so you can see what these actually look like in the real world. The first one is a capture test. A capture test tells us what percentage of aerosols get captured by a local capture device. So the device that you see in these photos are ventilated headboards that we've been putting into patient rooms. And we've been testing these to a criteria where they need to capture 90% of low velocity aerosols. So in order to test this in the field, it's kind of a two-part process. First, you need to measure the rate that you generate contaminants in the test condition, and then you go ahead and measure how well the device does in capturing those. In order to generate contaminants, we've been using these residential humidifiers. You can see them on the bed. You buy them at Walmart, and you fill them up with salt water, and that salt aerosolizes to fill the room up with particles. So you run one test with the humidifiers on and the ventilated headboard off, and then contaminate the room. That tells you how much contamination you're dealing with. And then you run a second test with the humidifiers on again, but also with the capture hood ons. And then you can see the capture effect based on that, the generation rate of what's happening in there. And our criteria here was 90% capture. We'll talk a little bit later about what 80% capture might look like, but that would be quite good too. In order to pass the test, we said that you have to capture 90% of the aerosols that are being generated right there on the bed, right? Now, the testing could be a little bit easier if you had a device with a known generation rate, then you could just use that. One of the guys we know in ASHRAE and we've corresponded with has figured out a calibrated generation device. It's a nebulizer that he uses isopropyl alcohol and salt. And so something like that could make the testing a little bit easier. We've done quite a bit of this testing though. Different versions of the ventilated headboard went into different med centers that we did. And we're also working with a vendor on developing a portable model that we could order and then store intermittently. So the way that we were normally doing this throughout the end of 2020 was we would set up a prototype in one room, then we would go out and then do the tests, and then come back home and do the math and print off the report. And if it passed the test, then we would proceed to scale. So at that point, if you pass the 90% test and you want to go do 20 of them in 20 different rooms, then great, go ahead. The second type of testing is called a containment test. And in order to do a containment test, you need to have 2 meters. You're going to contaminate a room pretty significantly and consistently for a period of time. And then you're going to take readings inside that room and then also take readings outside the room to see how well the room contains those contaminants. There's 2 scenarios that you can run this testing on. One is without traffic and the other one is with traffic. So without traffic just means that you're going to keep the door closed, contaminate the room, and see how well the room contains those contaminants. But in healthcare environments, just about all the healthcare environments that we deal with, traffic is a real thing. So I'm of the opinion that it's wrong to ignore it. So a containment test with traffic means that you're going to contaminate a room, simulate traffic in and out of the room while measuring that containment. Okay, so now let's talk about containment in theory. We do have some engineering theory on these. There's a guy by the name of Wei Sun in ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineer, who's been working on this for at least the last 10 years. So first up, we define this thing called barrier effectiveness. Barrier effectiveness, or BE. That's where we can actually say, hey, this door is 95% effective, or this anteroom is 99.5 or 99.9% effectiveness. That's the end here. Barrier effectiveness is defined as, that's how well we're actually doing with this barrier. And its definition is 1 minus the contamination ratio, or contamination rate. Actually, both words are used. So that's CR. And so there's the equation for contamination rate or contamination ratio. This is the one that looks scary because it has an interval. So you're thinking, oh, no, we have to do calculus. But calm down. Not really. We don't have to do calculus. The reason that there's an integral there is because we're talking about an area under the curve. So what we're going to do is measure contamination over time in both places. And you can see the figure on the right side of this slide. The ratio is basically the ratio of the orange area, which is small, to the blue area, which is big. So the orange area is the contamination level times time that's happening outside of the barrier. And then the blue area is contamination level times time that's happening inside the room. And the ratio of those is the containment ratio or contamination ratio. So that's exactly what we do during a test. We create a contamination event in a room, and then we measure what happens in both of those locations over time. Our most controversial finding in 2020 was that the negative pressure rooms, just negative pressure across a single door, is probably not the panacea of engineering controls that that it was advertised to be by some folks. And maybe the right way to say this is that we found barrier effectiveness of a single door to be between 95% and 98% with and without traffic, and also with and without negative pressure. In any room, which is 2 doors, and we did test that, shows more like a 99% effectiveness or a 99.9% barrier effectiveness. But the single door, kind of regardless of the negative pressure or the traffic, we were in that sort of 90-95% range. I say that finding was controversial. Really, it probably shouldn't be. This also comes from the research which he did in a lab in a very controlled setting. And if you look at this contamination ratio, in the middle of the chart here at 0 pascals, you can see that he basically found a 5% contamination ratio, which is a 95% barrier efficiency. In other words, a door with 0 pressure across it contains 95% of contaminants. And if you add a little bit of pressure, so if you shift over to -5 or to 5 on this chart, you'll see that the barrier effectiveness changes a little bit, but it only changes a little bit. It's kind of a 2% effect in either case. So your barrier effectiveness is going to move from 95% to maybe 97%. And so that's to say that in a lab, when we add a little bit of pressure across something, then we can see a 2% effect. In the field, where when we were out there doing field testing, we weren't able to measure a difference at all. We didn't see it at all. But that shouldn't be super surprising, right? It's not a huge effect that you're talking about. It might not show up in field testing. But of course, when you go into an ASHRAE meeting and say that to a room full of engineers, who were trained our whole lives that negative pressure is the greatest thing since sliced bread, then it's not very popular. So this sort of brings us to the third type of test, which is removal testing or fouling testing. And this is kind of the main event, folks. This is the big one. So the first type is this basic fouling test, where you go into a room, you foul the room with an aerosol contaminant, and then you watch as those contaminants are removed. So this is what some of ours look like. We take readings for about 20 minutes, and then we curve fit that data to an air change rate. If we need to, we multiply by the room volume to put it in units of airflow in CFM. So we're not actually measuring air change rate or measuring airflow in CFM, which is kind of what I hate about this. We're actually measuring contamination concentrations and removal. So when we say 2 air changes per hour, the effect that we're really looking for there is a 50% reduction in concentration in 20 minutes. When we say 4 air changes per hour, the physical effect that we're actually looking for there is 75% reduction in 20 minutes. So that vocabulary to say air changes per hour, when really what we're looking for is removal, is, to me, that's a little wonky. And hopefully that gets better over time. The other thing that happens in the fouling test in any room is mixing. And so in my overly simplistic mind, which matches the design models, right? It matches all the assumption in the design models. I would love to say that, hey, you can introduce a contaminant at any point within this room, and you should see the concentration fall 50% in 20 minutes, right? Based on the air change rate. Then that should be repeatable no matter where you introduce the contaminant in the room. But in reality, there's imperfect mixing, and there's another thing called ventilation effectiveness. These things very much exist. And so they're going to insert themselves in field testing. And so there's a couple ways to deal with that. If it's a small room, you may not have to deal with that. In a larger room, you can do multiple sensor tests where you set up 2 sensors in the room, or you can just take 1 sensor and move it around. That's the graph that you see on the left there. Move it into 3 places and see what the diversity is within the measurements as you move that thing around the room over time. Then there's the sort of what I'll call the more advanced version of that. The slides that you see on the right are stolen or borrowed from our buddy Tom Smith, who does a lot of work in lab groups. And what he does is he uses a 5-point sensor array at breathing height to characterize the actual dose in a room. So similar to what you saw in the containment testing, where we had to do calculus, the dose that anyone would receive in a room is defined as the area under the curve. So it's the concentration times the time. And so what Tom Smith is doing here is he shows the theoretical dose. That's the dose that the math says happens at 4 air changes per hour. And then he goes in and does the measurements at 5 points, looks at the average of those 5 points or the aggregate of those 5 points, and finds the actual dose and compares the actual dose received in the room to the theoretical dose that was, supposed to be received in the room, and defines that as a measure of ventilation effectiveness. Should be 1 or higher, right? Or I'm sorry, it should be 1 or lower, to say that rightly. So in the future, this is a very good process, by the way, that Tom Smith has. And you have to read it in a lot more detail. I'm giving it lip service here. As far as I can tell, he's the world leading thinker in terms of measuring contamination performance in an actual space. For the future, for critical environments, we're going to want to do this. But also in the future for environments where we just want to observe the basics of the effect, then I think we're going to want to do more of the basic fouling tests that we've been doing this year. Okay, so before we wrap up in part 1 of this presentation, which is about measurement and the different types of field measurement, let's talk about meters, and we'll talk about foulants, and we'll talk about testing. The most affordable meters that you can buy are these simple handheld CO2 meters and particle meters. Those can be had for about $100, $300. The CO2 meters also usually measure temperature and humidity. And at that price range, the particle meters are usually measuring PM10 and PM2.5, and you can buy some models that include PM1. We like to buy the ones that include PM1. They're the same price. The particle metrics in that price range are usually always in units of micrograms per cubic meter. If you want to look at particles and you can spend a little more money, you can get a 3-band particle counter that costs between $1,000 and $3,000. Those take a 1-minute sample of air and then give you particle counts in units of particles per cubic meter. The less expensive models there measure in terms of 0.3 microns, 2.5 microns, and 10 microns. The model that we got was about $800. If you're measuring particles in the room, and particles are going to be your contaminant of choice, then all you need to do is foul the room with a cost-effective and reliable source of particles. My personal favorite for the room fouling test is Aquanet hairspray. For a basic fouling test, hairspray works great. A 10-second spray of hairspray will foul the heck out of this room that I'm in right now. The downside to hairspray is that it has an initial velocity, so it comes out of that can with some force. And so if you're doing capture tests like the ventilated headboard or those 5-point tests, you probably don't want that. You're going to want a low velocity source or a no velocity source. And so that's where you would use the humidifiers or the nebulizers or something that, bubbles particles out rather than shoots particles out. So that's if you're dealing with particles. You can do these fouling tests with CO2. Believe it or not, I actually tried the high school science project thing where you do baking soda and vinegar to generate CO2. It does generate CO2, but don't use that for testing. It's very messy and it doesn't produce enough to foul even a small room. So dry ice is an option, and that's a very good option. Dry ice is CO2 in solid form. So that's pretty easy to work with. You just keep it in an airtight cooler, open it up when you need to foul the room with CO2. There are also some CO2 fire extinguishers that you can buy. I haven't personally used those, but some of the folks that we've talked to have been successful in doing tests with CO2 fire extinguishers. The big trick here is if you want to measure the effectiveness of a UV system. Remember, I talked about the difference between removal and deactivation, right? So if you wanted to measure one of those deactivation or disinfection technologies like UV, then you would need to use a biological agent. And measuring biological agents is a little trickier. There is a thing out there called a fluorescing particle counter that measures the particle count of living matter in the air by observing particles which fluoresce light. I've never used one of these, but there's some studies that use that technology. There may be some tricks with it because we don't know whether it can tell the difference between something that's living or something that has recently died. To use some crass terminology there that somebody can correct me on, by the way. Most of the validation of UV systems that have been done in the literature use specific biological agents, namely this biological agent called Microbacterium paraphytorium, which sounds like a Harry Potter curse to me. So what you do is you spray the stuff in the room, and then you take a sample, and then you wait a period of time, you take another sample, and you send them both to the lab to see the levels, and the math works the same way from there. Obviously, that's a more expensive and a complicated procedure. The other thing about just monitors and foulants and testing procedures is that at this point they require a little bit of creativity. A lot of the stuff is not written down, and so the stuff that we were doing this year, the stuff that Tom Smith is doing this year, it does require some thinking and some creativity. So I think this field will grow in time as we start to validate our controls. So to sum up on validation, we talked about 3 basic types of engineering controls and then 3 basic types of tests. Those were capture and containment and then removals. I need to add the asterisks to this slide before I present it tomorrow. And then we looked at basic fouling tests. We looked at contamination tests or containment tests, I'm sorry, barrier efficiencies. We looked at both simple and advanced versions of fouling tests. And we wrapped up by talking about contaminants to use for testing. So now we're going to switch to design. During design, what we need to do is predict the effects of the engineering controls, but more importantly than that, we need to assign those engineering controls based on how they affect risk. In order to do that, we're going to have to do some modeling, risk modeling. Now, there's a bunch of things wrong with modeling. We have to assume standard pulmonary ventilation rates. We have to assume well-mixed rooms. We have to assume equal vulnerability of the susceptible people. We have to assume the standard aerosol generation rates, exposure time. So that's a lot of assumptions. I'm sure you can see that's a lot of assumptions. And then, of course, once we start modeling, we could talk for hours and hours about which model to use. There's kind of 4 leaders to choose from. There's variations of each. Researchers have developed variations of each one of those. And we're going to use the highlighted one here, which is the Wells-Riley model. And we're going to use it for kind of one reason or one overriding reason, which is that it's really easy. It's a single equation. I think that's also the reason why it's really popular. You'll see that if you search the literature, you'll see that model used quite a bit. Before I jump into showing you some of these models, there's 2 more disclaimers. First off, any aerosol model is not modeling near field effects. So if you're within coughing distance or sneezing distance, don't rely on the HVAC system for protection. There's nothing that HVAC systems can do to help you in that scenario. That is not what's being modeled within these models. And secondly, these are environmental only risks. At least the ones that I'm going to show you. There are some models out there that attempt to include masks into the equations. What I'm going to show you are environmental effects only. So we're assuming no masks in this. Everything that you see can be made better by the wearing of masks. Okay, so this is a modeling tool. This is a comparative risk assessment spreadsheet. This slide has a link. So if you get a hold of this presentation or you get this in white paper form, there's a link. The tool is posted. It's in Excel. It's publicly downloaded. There's no password on this. This is a single page spreadsheet to take a look at one room and cross-contamination risks. So you can kind of see a little diagram up at the top there. We put the number of sources in the room, the aerosol production rate, the basic risk equation is sort of spelled out right on the page. And then the calculation really just has a few elements. You have the room ventilation rate, which is going to set the removal rate in the room. You have an exposure time, which is in minutes. There's a column in this spreadsheet called capture for a source intervention, like the ventilated headboards that we showed during testing. And then there's a column in here for barrier efficiency, where you literally just put in the barrier efficiency of the door, and that tells how much is going to go across the door. So that's the tool. Not a super complicated tool, which is why I wanted to show it to you. So let's look at some of these models. First model here is for a pretty long exposure time, like a 4-hour exposure. If you were doing an ICU nurse, or if you were an ICU nurse during a 12-hour shift with 3 patients, 4 hours would be kind of the time that you spent with each patient. So that's why we're choosing this 4-hour exposure time. We would kind of assume that that would be cumulative, at least in a day. And then when that provider goes home at night, then they hit the reset button. You're seeing 2 models here. The one on the left is for a disease like COVID. The one on the right is for a disease like measles. I don't know if you know this, but measles is about 10 times more infectious than COVID, maybe more. And so you can kind of see what those risks look like under the different scenarios with the different diseases. Just to talk through some of the options here, because you're going to see them again and again and again on the different slides. For room ventilation, we assume that that is effective. So it's actually giving us the removal rate. 2 air changes per hour will, in fact, produce 2 air changes per hour in a fouling test. 4 air changes per hour would, in fact, produce 4 air changes per hour in a fouling test. You'll see a line about halfway down here that says in-room UV equivalent to 4 air changes per hour. That means that we would be putting in a UV system, but that the UV system would pass a fouling test with one of those biological agents, right? I'm not a UV expert, so I don't know how to design a UV system that would actually pass a 4 air changes per hour fouling test, but that's what it means here in the model. And you would need to specify that test in order to validate it once you put it in. You'll see a few lines in here about local HEPA filters, local 500 CFM HEPA, local 1000 CFM HEPA. Those represent putting a scrubber in the room on the floor. And in those cases, we've gone ahead and in the model, we've assumed that those are only about 50% effective. So the 500 CFM HEPA only gives you about 250 CFM worth of room effect. That 50% number is something, it's very sensitive. It can be a lot worse than that, but that is something that we've sort of seen within our field test. It's never 100%, 50% is a good middle of the road there. Then down towards the bottom, of course, you'll see the ones that say 80% capture or 90% capture. Those are the ventilated headboards or the capture devices. We would assume that those would pass the 90% capture test or the 80% capture test. And you can see, by the way, that a local device with an 80% capture is very, very good. It does quite well relative to everything else that could be going on. Okay, so here's another model for a ward. If you clustered multiple infectious sources into the same space, then the risk is going to go up. This model is also calculated at the 4-hour exposure time. When we were working on one of these, we actually looked at what it would do at a 12-hour exposure time. So you can see what that looks like. That actually multiplies the risk similar to a more infectious disease. This model is for shorter stay spaces, so things like 20-minute exams, 1-hour procedures, 2-hour surgeries, right? An hour consultation, things like that. And you can see right away that for the shorter exposures, those risks are relatively lower. You kind of want to look over to the measles side to see some actual numbers, particularly, by the way, the idea here of transmitting across the door and creating an infectious aerosol risk for somebody in the hallway. With COVID, you can't even see the orange bars on this chart. You would need to be dealing with measles to see something like that. Another big disclaimer for this slide here is that once you get into procedure rooms or operating rooms with laminar flow, that perfect mixing assumption is really inappropriate. So there's asterisks next to those. That's the downside when you're thinking about those rooms. The bright side when you're thinking about those rooms is that they're very, very well ventilated spaces. And so any way you slice it, that risk is going to be pretty low. A couple more sheets in here. This sheet is for system risk. In theory, aerosols can leave a room, travel through an HVAC system, and then create a risk for somebody who's in another room. The key variables here are the number of infected that are on the system, as well as outside air dilution and filter efficiencies and other system interventions. But there's basically the size of the system is the biggest variable that you'll come up with. If you have one source that's on a small system that serves maybe 2 rooms, then you can see significant risks here. But if you have one infectious source, on a large system that serves a floor, then those risks are going to be much, much, much lower. So we get asked this quite a bit, actually. Oh, should we change out all the filters in our system to this level, or should we put HEPA filters in all of our systems? And so the answer to that is, if those systems are larger systems, then the benefit of bumping up that second level of filtration is really, really small, or kind of immeasurably small. And that is a little that's a little characteristic of healthcare. In hospitals, we tend to have large systems, 10,000 CFM systems, 20,000 CFM systems that serve a floor or more than a floor. And so it's really already handling that risk. This is a model for outdoor worker risk, which has actually been talked about quite a bit. Worst case scenario is that you would have a host in a room with very poor ventilation in that room and a high concentration, and then you exhaust it to the outdoors, and you have somebody standing, 2 feet away or 5 feet away from that outlet, and standing there for a full hour. And even there, those risks are relatively small. And this model, well, they're relatively small on the COVID side. On the measles side, you could see some risks. Even there, those risks are kind of relatively small. This model is a bit of an it is an oversimplification that we can't walk line by line through the calculations. Basically, as you discharge air to the outdoors, then move away from it, we have an equation to calculate a thing called dilution factor, that's DF, which is a function of the distance and the velocity of the air coming out of the outlet and the direction of the air coming out of the outlet. The engineers, the equation for that dilution factor comes from ASHRAE 62, Appendix B. That's where you have to find it. And if you're working on one of these, you're going to need to spend some time with that calculation method. There is actually kind of a worst case case scenario where the exhaust is blowing right into the face of the receiver. So conceivably, you'd just be standing there right at the outlet, with your mouth open, going, it's blowing air in your mouth. My son would do that, I think. So maybe that's not a totally outrageous scenario, but I didn't include that in the modeling. Okay, there's one more model in the spreadsheet at this link, and that is it's kind of the most complicated, so I'm not going to try to walk through the math, but this one is for residual risk. Residual risk is when you have, first off, you have a provider in the room with a source of aerosols for 20 minutes, and there's a certain ventilation effect that happens while they're in there together. Then the infectious source leaves, somebody else walks into the room a period of minutes later and stays in the room for 20 minutes. And if you remember, we talked about the dose received being the area under the curve of contamination times time. Well, that concentration is constantly going down with time. And so the residual risk is something that drops off, with time. I think this is an important analysis that actually I haven't seen anybody else do. What a lot of people are looking to is they're looking to the CDC table that tells you this is how long you have to wait for 99% removal of contaminants or 99.9% removal of contaminants. This is also very simple math, but I think it's important to point out 99% reduction in contamination is not the same as 1% risk. Rather, risk is a function of that concentration. So the maximum risk in the room occurs while the source is still there and the provider is there. The residual risk can never be that big and always falls off from that point. So if we had 100% risk in the room while the provider's in there, it's a provider and the source are in the room together, there's 100% risk for the provider. Then it might be true that reducing the contamination down, 99% would get you to a level of 1% risk. But that 100% risk for the provider is never true. And so it's always better than that, right? The 1% risk line is reached quite a bit sooner in really every scenario. I know this might look like a sacrilegious piece of analysis here because ostensibly it looks like I'm conflicting with the CDC table. But I don't think it is a conflict because the CDC table says in its title, this is the time required for airborne contaminant removal, right? The CDC table doesn't say anything about risk. And so if a reader is looking at this table thinking that it's about risk, that's kind of an incorrect reading. It's totally understandable. I think nearly everybody in the industry is doing it. We've seen policies written around this table, but that's not actually what the table is, and it's not actually what the table says. Okay, so you may be saying to yourself, wow, I like this idea of modeling, but Travis, your models are terrible. I hate your spreadsheet model. It's totally unscientific. Everything in there is wrong. And to that, I would respond, great. Don't use those models. They're publicly available. You're free to use them. But if you don't like them, use some other ones. And there are other ones. They're actually springing up pretty commonly now. So over on the top here, airborne.cam, which is not a misspelling, it's .cam, airborne.cam, is from a team in the UK. And there's another one down at the bottom, the tinyurl/COVID-estimator. That comes from the University of Colorado Boulder. There are more. You can do a search today and you'd find about 3 or 4 more that are out there within a Google search. And then I'm giving this presentation in May of 2021. So if you're watching this on a recording, in June or July of 2021, there's probably more then. So go ahead and do the search and you will definitely find more. So let's recap a little bit on design here. I've shown the risk assessment tool. This one that I've shown you is free, is available. There are other ones that are free and available. If you don't like the one that I've shown, you may in fact think that the tool that I showed you is the second worst tool in the world, but I would say it could only ever be the second worst tool in the world because the worst thing, the absolute worst thing that engineers could do is no modeling. Which is frankly what most of us are doing now, and that's what all of us did throughout the year 2020. In my opinion, that cannot be acceptable in the future. In this hour, we did show those models. We showed a couple of those models: single room assessments, ward risk assessments, short stay assessments, system risk assessments, outdoor worker assessments, residual risk assessments. And within each of those models, we saw options for filters and capture devices and ventilation rates. And each one represented the predicted behavior of aerosols in that engineering control. Just to be blatantly clear, the local capture options and the local treatment options, which are often low cost and portable and interchangeable, they perform extremely well. They usually actually perform better than things like increasing air change rates, adding infrastructure, or adding negative pressure, right? Which brings us back to this. They perform better because they're smart. So architects and engineers who are looking towards the future and asking yourself, do we need bigger air handling systems? Do we need to put HEPA filters in all of our units? Do we need to add a bunch of negative pressure controls or interchangeable rooms that we can convert to negative pressure? No, that's more. And more is not necessarily better. We don't need more. We need to be smarter. We need better engineering tools. We need more quality control we need more quality in our contamination control engineering. We need to stop teaching young engineers about air changes and negative pressure and start teaching them about contamination control and risk assessments and how to validate those controls when you install them. We need better explanations. We need better comparisons. We need better predictions. We need higher reliability. If we do an intervention, then we need to understand the base case. We need to be able to rank options. We need to be able to size interventions for the applications. And then we need to make those controls reliable. They need to earn the title of an engineering control with the reliability and repeatability that they bring to the table, which wraps us all the way back to the testing and back to where I started. Every engineering control that we deploy should have a measurable effect on the behavior of aerosol contaminants. We should be able to predict that effect during design, and then once it's built, we need to validate that effect by physically measuring it. In my conversations with infectious disease and doctors and infection control and environmental safety, they hear the words engineering control and they expect reliability and repeatability. Today, tomorrow, or next year, we should be able to walk into that room and witness the same effect on those aerosols without deviation and without fail. That way, when an aerosol disease does walk into the room, we can rely on that effect occurring without deviation and without fail. And to my fellow engineers, we need to rise to that expectation. That is not where we were playing ball in the year 2020. And that's where we need to get to in the future.